My name is Stella Nakazi, and I am going to talk about the mechanical hand project being presented by Group 3. Basically, this project, we are taking it in this summer class for Engineering 1201 by Professor Meredith Wren. And the entire point of the project is to create a hand, like a prototype that's almost similar in function to the human hand. The team members are Dana Jackson, and she's the team leader. Me personally, Stella Nakazi, I'm in charge of the PowerPoint presentation, like writing it out. Susanna Lopez-Herrera in charge of videography. Ryan Rowland in charge of data compilation. Joe Morales in charge of report writing. And we have all come together as a group to share our knowledge in what we think can be done best to better our project and achieve the questions at hand. So, introduction. The mechanical hand project will be studying the actions of a mechanical hand and how best it carries out its functions, and if in any way it can imitate the human hand. The materials being used are rubber bands, cardboard, thread, string, tape, glue, scissors, ruler, paper cutter, cups, a die. Obviously, the cups and the die are what we're going to be using towards the end when we have to execute a few tasks that were presented to us. Yeah. But the rest is mainly for creating the hand itself. And introduction part 2. The human hand is used for various day-to-day activities and tasks. It's used in washing dishes, writing, lifting items from one place to another, and of course, even though it seems to be working alone, it's just a vessel holding together some of the parts of the muscular and skeletal systems. It's comprised of tissue, bones, and ligaments. The bones are skeletal parts, and the tissue and ligaments are part of the muscular parts of the hand. Functions of the hand are controlled by the somatic nervous system. In this project, the functions of the hand are going to be controlled by the group members with use of components that mimic the function of tissue, ligaments, and bones. In the next few slides, we're going to be talking about the different steps we undertook in this project and how we have been able to realize those steps.
We want to introduce ourselves and kind of give you a little bit of a view of what we've worked on. But first off, need to recognize the human hand and just how masterfully engineered of a natural device it is. The human hand is quite remarkable in the fact that it can work in very precise detail, yet at the same time do intense grips and use extreme force whenever necessary. The harmony that is found in the working human hand, the bones, the tissue, the skeletal muscles, tendons, nerves, joints, all work together in a very remarkable way to function. In the event that an individual does lose their hand, you could find it quite challenging to actually be able to come up with an artificial hand that is able to mimic all of the different functions that the human hand can actually perform. So this is a big undertaking for anyone, but especially in our situation when we were limited to 4 different items: the cardboard, string, rubber band, and the plastic straws. We set out to construct a mechanical hand. So the first thing we did is we did a rough outline of our hand, and we used the razor blade to cut out on the cardboard. And then the next thing we did was we used a ruler to actually create our creases that represent the knuckles, represent the joints in the fingers and the thumb, so that we could get that bend. And then the human hand has numerous bones. This is not near the amount of bones that the hand actually has, but we use the plastic straws, cut them so that they represent the bones. Found that in doing so, We need to make sure that the straws are cut short enough so that whenever you bend the hand or the finger, it does not, they're not too long to where they actually rub, preventing good range of motion. And at times we actually saw that if whenever they were too close, the string would actually cut through the straw. So we had to redesign that, and we had to make smaller cuts of our straw representing the bones. The strings come down because actually in the human hand, there's the muscles that actually do the work of the fingers are found in the forearm. And so that's what these, you'll see that the string is working to do. This is actually our next, this is the latest model we have of the human hand. And we added, you'll see we added much reinforcement. We added a place for us to be able to use our actual hand to make the fingers function. And we got this reinforcement around the wrist. Another thing that we did a little bit different is we set the thumb out so that it's a little easier to grip, and we're able to do the thumbs up. And we also decided to put rubber bands on the tips because the rubber bands actually added as a little bit more of a grip, which assisted the use of the mechanical hand so that we were able to perform the functions. So this is where we are right now in our mechanical hand. Thank you.
Hi, my name is Ryan, and I'm going to be presenting over the calculations, data, and tables that we have so far. Because we are so early in our presentation, we don't have a lot of data to go off of, but we have anticipated a lot of things to come, and that's what I'm going to go over right now. So this first slide covers the engineering calculations used. Of course, we're using force because we have to pick up objects, and force is described as the amount of force it takes to move 1 kilogram of mass at a rate of 1 meter per second squared. Stress is going to play into it once we finalize our project, because the issue we're having right now is we can't pick up anything using our hand, and that is because the hand collapses anytime we try to use it. So we need to address the amount of stress that's being placed on the material itself, and pound force will also play into that as well. And after that, we have our table of data where you can see our measurements for our length in the first phase, second phase, and our current phase. We had to adjust the wrist by a little bit. It didn't have to be so big as it was at first, because it wasn't providing structural integrity. Being bigger, it just needs to be thicker, which we're going to address in later models. We also had issues with the thumb. We thought at first the thumb being long would be a good idea, but we realized it just closes in and collapses in on itself. Same thing with the straw pieces. The straw pieces were a little too long, and once the finger would start to close on itself, it would interrupt the movement, and they would crush against each other, restrict how the hand could collapse on itself. And so that became kind of an issue as well. And the string has been pretty consistently the same length. It hasn't affected a whole lot. The whole hand also has been relatively the same throughout, as well as the fingers, disregarding the thumb. They have all been approximately the same as well. We haven't noticed a big difference changing those or doing anything with the fingers themselves. Now, the way the object's used, we're taking the measurements now so we can address stress later down the line, as well as the force needed to move these objects. So our die is 0.004 kilograms or 4 kilograms. The cup is 15 kilograms. The box is 21 kilograms. The golf ball is 46 kilograms, and the fill cup is 69 kilograms. So that is what we need to overcome Of course, the die being the smallest, the filled cup with the chips inside is going to be the biggest. So we have to make sure our hand can handle those weights and then dump them into a cup or move them in regards to the boxes, stacking them. And the same thing with the die, we need to be able to move the die around. And that is it for me.
Good afternoon, everybody. This is Joe Morales. My demo video will be to discuss the conclusions and results of the mechanical hand build, as well as the task that we were supposed to perform once the hand was completed. Through a series of trial and error, we started first with stacking boxes. This was probably one of the easier tasks. It wasn't recorded, but we successfully completed on 2 tries, taking the mechanical hand, gripping one box, and stacking it on top of the other. The second task was performing a thumbs up with the mechanical hand. So to do that, the hand we developed strings to put through the mechanical hand, and that controls all of the finger points, the fingers, and the thumb portion. So our mechanical hand had a puncture where a straw goes through, and from the tip of the thumb, the string that was tethered to the top was drawn through and to the back of the palm, down to about the forearm base. Once we did that, we're able to take the string, pull on it back, and then successfully create a thumbs up. That only took 2 tries also. The next task, which was a little more difficult, was to transition the contents of a cup inside of a cup, take it, and pour it into another cup. So the contents that we used were 2 wooden chips. So we placed the wooden chips inside the cup, and we have video recordings of us gripping the cup with the mechanical hand by pulling on the strings, gripping the tops of the cup, able to carry it, and then pour out the contents, which were the wooden chips, into the second cup. That only took 5 tries. And moving on from there, then we had to pick up a die and turn it on its face to show a different number, and then put it back down to show another number. Oh, I'm sorry. We had to pick up the die, show a number, and then all we had to do was just place the die back down. This was a little more difficult, seeing as how the die was a much smaller object to grip on. So it took about 17 tries to get a successful outing of it. But thanks to the rubber band tethered grips on the top of the fingertips, we were able to place the die between the index portion of the mechanical hand, the index finger portion of the mechanical hand, and the thumb, turn it over, show the number 6, and then place it back down over on top of number 1. And that is video recorded as well. So then, for the last task that we had to complete, was we had to take a golf ball and we had to pick it up with the hand and transport it to a specific distance away and put it down. This one was probably the toughest task, just because the golf ball is a smoother surfaced object, and since the mechanical hand is made out of base materials like cardboard and such, it's a lot harder to get a solid grip onto it, pick it up, and travel it to a certain distance. But we were able to complete that task, but it did take 21 tries. So this was probably one of the toughest challenges that we needed to complete, but it was done so. And overall, basically, we showed that we could build a successful model of a mechanical hand using just the base materials that were given to us. So yeah, that's pretty much everything and all for now.
Hello, I'm Susanna Lopez-Herrera, and I'll be going over the recommendations for the future model. After thorough research, we realized that we would have to improve on the design detail and specifications of the model. We ran into issues with grip, especially with the golf ball, the cup, and the die. We were able to complete the task. However, it took us many times, as seen in our results. And we were thinking about making it more reliable than it currently is right now. And the way we thought about it was to increase grip, to add rubber bands around each finger so it can hold onto the ball, the cup, or the die. For the ball, it's really heavy, so trying to keep the ball between these two fingers was increasingly hard. The idea was to probably be able to pick up with all the fingers. However, the fingers were not long enough to be able to complete the task. So maybe by increasing the length of the fingers there, we can also increase our chances of holding onto the ball while we transport it. As for the cup, you will see in the later video that we pick up the cup from the top and not from the side. This is because when you pick up a cup, you wrap your fingers around the cup like this. However, our fingers are not long enough to wrap around a cup, and the width between each finger is also very small and made it impossible to hold and grip the cup like that. So we went over to spill the contents. For the die, what we did is we tried to pinch the die, then flip it over, then put it back down. However, that was really hard because you had to not only pick up the die with such a small area with little to no grip, but also turn it around and then put it back down. We ran into the issue that when we were turning it around, it was pretty difficult because of the way the hand was just designed in general. And to pick up the die, I think rubber bands, again, would be the solution. I mentioned a second ago about the usage of the hand and how it was pretty difficult just in general to use the hand because the hand needs support, hence it comes from the wrist. And so we put cardboard on the wrist and the base. However, that made it really difficult to operate with the hand and while using the strings. So maybe removing the base of the cardboard at the bottom or finding another way of doing that. Also, the strings for the fingers, for the 4 fingers went in the front and the thumb went for the back. For the 4 strings in the fingers, they kept on getting tangled and they were really hard to operate with because every time you were going to use the hand, you had to individually figure out which finger is which, and then if you were using it and forgot which finger, what string was for what finger, and it got tangled in, you'd have to start that process over again, making it more less time efficient and just frustrating in general. So maybe creating a little base to keep the strings separated for easier usage. Also, the strings also cause problems in the straws, how every time, if the straw was too big, every time the string would rip the straw in half and we'd have to replace it. So by making the straws and the fingers smaller, we can make the fingers bend easier and save us time with the amount of times we had to replace the straws. For now, those are the issues we have encountered with this current model. If most likely more are going to come up, but for now, these are the issues and our ways or our ideas currently in how to fix it. Thank you and have a nice day.
Okay.
Because even if you just turn it slightly.
Holding it sideways.
It's
Does that
because the
work?
fingers are too long, too short, so I'm trying to problem solve. Oh no, problem. If I can like,
We poured it.
Yeah, like picking up everyone.